On Friday, we learned about two more types of nuclear reactions. We had already learned about radioactivity, which is a process whereby a nucleus decays and it ends up resulting in transmutation, the conversion of one element to the other. On Friday, we learned about nuclear fission and nuclear fusion, two more types of nuclear reactions, which can also result in transmutation, the conversion of one element to the other. Now, fission, if you remember, was the splitting up of a nucleus. We got one heavy nucleus splitting up into two or more lighter nuclei. And then fusion was exactly the opposite. That's where we had two light nuclei, two really, really light nuclei, fusing together to form one heavier nucleus. Now I get two reactions up on the board here. We put the same ones up on the board on Friday, but it's been a little while now. Probably don't remember these specific reactions. I want you to identify for me which reaction is a fission reaction and which reaction is a fusion reaction. Okay, is the first one fission or fusion? Second one, fission or fusion. Tell me which one's fission first. Harry? Fission is the bottom one. We know that why? Good. You got one large thing becoming two lighter things, two smaller things. Now, in the end, there's neutrons there as well, and they're important. They're really important, especially in fission. But when we're trying to determine what kind of reaction it is, we don't pay any attention to the number of neutrons. Okay, we're just looking at the uranium and the krypton and the barium or whatever other elements it is. So one thing becomes two things. That's going to be nuclear fission. Nuclear fission can undergo a chain reaction. Chain reaction is a self-sustaining reaction, a reaction in which just keeps going. We get it going. We kind of prod it into starting, but then it keeps going itself. How does it keep going? How does it sustain this chain reaction in a fission reaction there? Cool? Was your head up? No? Anybody else? How does it sustain itself? Yep. Good. These three neutrons that are produced can potentially collide with more uranium and cause 3 more reactions, which can potentially cause 9 more reactions and so on. I'm not trying to suggest to you that every single time we have a reaction that all 3 of these neutrons will react with 3 more uranium nuclei, and then 9 and then 27 and then so on. Okay, it's not necessarily going to be absorbed, but we have that potential to happen. Okay, if we design this system correctly, mechanically, then we can kind of prod. We don't have to fire those neutrons at the uranium, but we can kind of direct them at the uranium. Okay, so we're not necessarily going to get all 3 reacting, but we can potentially get all 3 reacting. And again, that's what sustains the chain reaction. What about up here? This one's going to be fusion, but besides the fact that you can identify its fusion by process of elimination, how would you know that this is fusion? What in there, independent of what we just did, tells us that this is nuclear fusion? Parker? Good. You got 2 lighter things becoming 1 heavier thing. 2 heavy isotopes of hydrogen, H2, fuse together to form 1 heavier helium-3 and a neutron, which of course isn't important to determining what kind of reaction we have, but is important in terms of balancing out that transmutation equation. What's the problem with getting this going? Why do these hydrogen nuclei not want to fuse together? They do fuse together. They fuse together all the time. We look up in the sky, we see the sun. That's the perfect example of nuclear fusion taking place, right? It's a giant nuclear reactor, which is always undergoing nuclear fusion. But why do they not want to get together? Yeah, they repel each other. They're positive. All nuclei are positive, right? But not all nuclei are trying to get together. These are. Okay, these hydrogen nuclei, we're pushing them together. They're coming close to each other. There's a force of repulsion that keeps them apart. And that force of repulsion, you guys know from Coulomb's law, gets bigger as R gets smaller. R gets smaller, F gets bigger. In fact, as R gets really, really, really small, F gets really, really, really big squared. So that means that force of repulsion becomes astronomical. We actually have to overcome that force of repulsion. We do that by adding a little bit of energy on this side. Pump energy into it, usually in the form of heat. Okay, these things become so energized that maybe they can overcome that force of repulsion and then fuse together. How do we sustain this reaction? Okay, the chain reaction down here happened because of the neutrons potentially getting absorbed by more uranium. How do we sustain the one on the top? How does it become a chain reaction? What do you need in order to keep it going? Andy, your hand up? No? Can you answer it anyways? Yeah, it's the energy. Right? It's not all of this energy. Some of this energy goes into causing more of the reaction to take place, and some of that energy goes off usually in the form of heat. Look up in the sky. Okay, see the sun. There's a lot of energy being released from the sun, but some of the energy that was released from the nuclear reaction taking place in the sun actually goes into causing more nuclear reaction, right? The sun sustains its own nuclear reactor because it's so hot. Some of the energy that's released becomes a reactant, if you want to call it that thing in chemistry way terms. It becomes a reactant to cause more of it to happen. All right, we defined another term on Friday. We called it mass defect. We're going to define that in two ways today. The first way is the way that we defined it on Friday. It's the difference in mass between the parent and the daughter nuclei. In other words, again, if you want to think of it in chemistry terms, it's the difference in mass between the reactants and the products. You always lose mass. The parent always weighs more than the daughter. The product always weighs less than the reactant, if you're thinking it again in chemistry terms. But there's another way we can define it as well, which is going to seem completely different than the first way, but really is fundamentally the same. In fact, it's the second definition that actually leads us to the first definition. It's the difference in mass between the nucleus and nucleons. What's a nucleon? It's a proton and neutron. A proton is a nucleon. A neutron is a nucleon. Now, boy, this really doesn't seem to make sense. If the first definition doesn't make sense, hey, we lose mass in this reaction. How do we lose mass in the reaction? If that doesn't make sense, think about the second one. Let's say we got 25 people in this room right now. We add up the mass of you, everybody else. We add up the mass of all of us in this room, and we should get the total mass of the people in the room, right? But we don't. The mass of all the people in the room combined ends up being more than the mass of all the people in the room combined. If we add up the mass of everybody, it ends up being more than the total mass of all the people in the room. That doesn't make any sense. When we're talking about in terms of the analogy, of course it doesn't make sense. It shouldn't make sense. The mass of all the people, if we add them up, is going to be equal to the mass of everybody in the room. But when you look at it in terms of the atom or the nucleus, when you add up the mass of all the protons and add up the mass of all the neutrons, it's not the same as the mass of the nucleus. It's not. It's more than the mass of the nucleus. The nucleus doesn't weigh as much as the mass of all the protons and neutrons combined. It's because of an energy thing. There's kind of an energy stored in there. And of course, we learned that energy and mass are two different forms of the same thing, right? So if you're missing a little bit of mass in there, there's an energy stored in there, then total it can add up. But mass, it doesn't add up. Okay, the mass of the protons and neutrons isn't equal to the mass of the nucleus itself. And again, that sounds different because we don't even have a reaction in number 2. But this definition is what leads us to the first definition up there. That's why the daughter weighs less than the parent, is because the mass of the protons and neutrons combined is different than the mass of the nucleus itself. Binding energy, another term. Binding energy, we can define in a number of ways as well. We'll define it in one way. We're just going to say binding energy is the energy equivalent of the mass defect. So if you've got a mass defect of 10 to the minus 27 kilograms, well, we know that energy and mass are two different forms of the same thing. So the energy equivalent to that of the missing mass would be the mass defect. It manifests itself usually for us, okay, and manifests itself in a number of different ways. But for us in Physics 30, it manifests itself as the amount of energy that's released in the reaction. It's also Okay, of course, responsible for the difference in mass between the nucleus and the nucleons. But usually for us, again, it manifests itself as the energy that's released in the reaction. Now, how do you think you'd find binding energy? You got a mass defect, you got a missing mass. Okay, where did that mass go? Oh, it went into energy. How do you think you'd find the amount of binding energy, or that energy that's equivalent to the missing mass? We saw this equation once before. You guys know this. What is it? E equals mc squared. Take the binding energy, take the mass defect, multiply it by the speed of light squared, it gives you the binding energy, right? The energy that's released in the reaction. 3 units down at the bottom of the page, and then we'll do an example that relates this whole binding energy to mass defect thing. Does anybody recognize this unit from chemistry here, a U? No? You don't learn that in chemistry? Do you learn the term AMU in chemistry? Yes? What's an AMU? Yeah, and what's an atomic mass unit defined as? Remember? No? A U is just another symbol for an atomic mass unit. And the atomic mass unit, whether you call it a U or an AMU, is defined as 1/12 the mass of carbon-12. So if you take the mass of carbon-12, the whole thing, you divide that mass by 12, you're going to get 1 atomic mass unit. And the value of 1 atomic mass unit, this is on your data sheet, so you don't need to remember the number, is 1.66 times 10 to the minus 27 kilograms. You multiply that number by 12, it'll give you the exact mass of a carbon-12 nucleus. Now, I'm going to be honest with you. I think it's unlikely that you'll have to use that term on an exam, an atomic mass unit. But if you do, okay, you got the conversion factor here. It's on the left side of your data sheet. 1 atomic mass unit is 1.66 times 10 to the minus 27. Set it up as a ratio if you ever have to convert. 1 atomic mass unit over 1.66 equals, I'll set up your ratio on the other side, atomic mass units over kilograms, and solve for what you're looking for. Okay, I don't think you'll see that, but we're going over it just in case, because it's one of those objectives that we have to know, and you never know whether we're going to see it or not. We're going to do an example in a few minutes that will use atomic mass units, even though I doubt you'll end up seeing that on an exam. These bottom two, hey, I'm pretty sure you're not going to see those on an exam, but again, we got to know them, so I'm going to go through them real quickly here. Just not going to spend a lot of time. Mega electron volts per c squared, giga electron volts per c squared. We look at these both and we think, oh, that's energy, right? Electron volts is energy. But energy over c squared isn't energy. Energy over c squared is what? Mass. So these units measure mass. That's the big thing that I want you to take away from that, is that these units measure mass, not energy. Now, in the highly unlikely event that you actually have to use those units for mass, here's the way I want you to figure out what it's equivalent to. Everybody take a look at your data sheet right now. The back side of your data sheet, bottom right-hand corner. Near the bottom right-hand corner, it has this heading called First Generation Fermions. We're going to learn about the last of these fermions on Thursday of this week, but we already know about 2 of them, the electron and the positron. It says for the electron, the charge of the electron is minus 1e, where we know that that means minus 1 times the elementary charge, or negative 1.6 times 10 to the minus 19 coulombs. It says for the mass of an electron is 0.511 mega electron volts per c squared. Again, that's mass. We just learned that, right? It's mass. But you know what? We know the mass of an electron in kilograms already. We know that it's 9.11 times 10 to the minus 31 kilograms. So I doubt you'll ever have to use mega electron volts per c squared. But if you do, then here's how you're going to convert. You're going to go to that number, put 511 mega electron volts per c squared. The mass of the electron in mega electron volts per c squared. You're going to say that is equivalent to 9.11 times 10 to the minus 31 kilograms. And then you're going to set up the ratio just like you do for converting electron volts to joules, converting atomic mass units to kilograms. Okay, just set up the ratio. It's just a little bit harder to find the ratio here. Okay, there's nowhere on your data sheet that says 1 mega electron volt per c squared is equal to this many kilograms. But if you look around your data sheet, there's a place where it says this number of mega electron volts is equal to this many kilograms. That makes sense? We're not going to spend any more time on that because I don't think it's going to be something you're going to see. But you know how to deal with it just in case, in the unlikely event that you do have to deal with it. Okay? Sometimes they surprise us, right? 20 years in, still, I look at a diploma exam, and there's still sometimes a little surprise. Hey, didn't expect that. What we try to do is cover all our bases, just in case we do see some of those surprises, okay, so that we can deal with those surprises. But we're not going to spend a ton of time on it. Good? Okay, let's do an example here. To do that example, we're going to need a table that appears on page 881 of your textbook. And to do a couple questions that you have for homework that relate to that example, you're also going to need that table. So you might want to write down in your notes right now, table page 881. Because otherwise you're not going to be able to do your homework tonight. I think that's an appendix. If you haven't downloaded the appendix of your textbook yet, then you might want to do that. Okay, this question says, calculate the energy that's released in this fission reaction. Listen, we know this is fission because one heavy thing becomes two or more lighter things. You got some neutrons in there, but they're irrelevant in determining what kind of reaction it is. Just look at this. One heavy, two lighter, got to be fission. We knew that already. We didn't need to be told that. But we don't know how much energy is released. Let me ask you a couple questions before we start figuring this out, though. Where does the energy released in this reaction come from? It's a two-word answer. Where does the energy released in this reaction come from? It doesn't come from nowhere. You can't create energy from nothing. I'm going to give you a hint right now. You can create energy from something other than energy, but not from nothing. Where is the energy that's released? Josh? It comes from mass, the mass defect, right? So why don't we, in this question, find the mass defect? Let's get the mass defect. To get the mass defect, the difference in mass between what we start with and what we finish with, we're going to get the mass of everything. What's the mass of uranium-235 in atomic mass units from page 881? And the mass of a neutron in atomic mass units is 1.00 for the neutron. 1.008. Keep going. 665. All right, good. That's it for the left side. Let's get the mass of the right side components here now. Barium-141 has a mass of 140.14412, thank you, in atomic mass units. Krypton-92 is 91 point. Hey, notice uranium-235 was 235 point something. Barium-141 is 140. Krypton-92 is 91 point something. Do you notice that the mass number on the left side, the actual mass is bigger than the mass number? On the right side, the actual mass is smaller than the mass number? Not a coincidence, right? We know we have to lose mass here. And if these numbers aren't smaller, then we're not going to lose mass. We're not going to have a mass defect. What does that work out to be there? 91 point. Thank you. And of course, our three neutrons, we have 3 times 1.008665 atomic mass units. 3.0. Thank you. All right, now We're going to say this side of the room, Colin's side of the room right here, is going to find the total mass of the left-hand side. And we're going to say here, Garrett's side of the room is going to find the total mass of the right-hand side. So everybody here, take out your calculators, figure out the left side. Everybody here, take out your calculators, figure out the right side, please. James, what's the mass of the left-hand side there, please? 0.52595. Thank you. And the mass of the right-hand side here, Tara? Cool. Does this number seem to make sense? Is there anything that jumps out at you as being an indication that maybe we're right on these? What do you know about the mass of what we start with versus the mass of what we finish with? Gary? Yeah, the mass on the left has to be bigger. We have to lose mass, right? Did we lose mass? Yeah, we have a mass defect. Let's find the value of that mass defect now. We're going to do that by subtracting the two. It's going to be 236 minus 235. It's going to give me 0.186032 atomic mass units. Hey, before we go any further, let's convert this to kilograms, hey? Could we have converted all these numbers up above here in green and red to kilograms? Sure we could have. Why did we not need to? Yeah. Yeah. Yeah, exactly. We're adding and subtracting numbers. It doesn't matter what units we use when we're adding and subtracting numbers. It just would have made more work if we had done it up there. We could have done that. Hey, it's fine. Okay, but it's quicker and easier, less work if you do it down here. So let's convert that to kilograms now. We know that one atomic mass unit is 1.66 times 10 to the minus 27 kilograms. Okay, that's what it's defined as on our data sheet. We know that 0.186032 atomic mass units is equal to X kilograms. Let's get that value right now in kilograms. What's it we're going to be? That's going to be, I was going to say atomic mass units, but that's going to be kilograms, right? That's a really small number, right? Really small number. The mass defect should be a really small number. We're talking about a single reaction here. Now, when the atomic bomb was dropped on Hiroshima, we had much bigger mass defect than 10 to the minus 28 kilograms produced, which of course released a lot of energy. Why? Well, because it was a chain reaction taking place. It was one reaction, then 3, then 9, then 27, then 81, and so on. Okay, here, we've got one single reaction with one single small amount of mass defect. All right, finally, we want to calculate the energy that's released here. Equals mc squared. It's going to be 3.0881312 times 10 to the minus 28 kilograms. And we want to multiply that by 3 times 10 to the 8 squared. We get 2.779 times 10 to the minus 11, and that would be what units? Joules. We use standard units, kilograms, meters per second. We're going to get joules out of it. Now, that could be fine. If you're given an answer in joules, you're good to go. But what if you're given your 4 options in electron volts, so you've got to convert it? We know how to do that, right? We've done that since unit 2. 1 electron volt over 1.6 times 10 to the minus 19 joules equals X electron volts over 2.779 times 10 to the minus 11 joules. You take the 2.779 up, and we get a number of electron volts. Done. Make sense? Now, when you look at this, there's a lot of numbers here, right? There's quite a bit of work and a lot of numbers. You're going to have 3 questions for homework. Really, it's like 2. One question is kind of split up into questions 2 and 3, so it's really like 2 questions that are like this. In the end, if you just try to do it brute force and you're not thinking about it, then you're probably not going to be able to solve them. But if you just allow yourself to think and allow yourself to use a little bit of logic, I think this makes perfect sense. Right? We want to find energy release. Where does it come from? Mass defect. Well, where does mass defect come from? The missing mass. Well, then let's find the missing mass. Let's find the mass of what we end up with versus what we started with. Then let's multiply that by that missing mass by c squared. And then let's, if we have to, convert it to electron volts. We're done. Right? The two questions that I want you to work on for homework, three questions, but really 2 and 3 are part of the same thing. Page 819. You're not going to have a chance to work on those right now, although you might a little bit later in class. Just please, as you're working on those for homework, please keep in mind, please keep beside you the example that we just did. Keep beside you that example. And you know what? You do a couple more problems like this, I think the logic will make perfect sense to you. And as long as it does, you should be able to do this on a test. All right, I want to do right now just one more question before we take a bit of a break here. We'll just do this as a group here together. It says, in 1939, 4 German scientists made an important discovery that ushered in the atomic age. They found that a uranium nucleus, after absorbing a neutron, splits into 2 fragments that each have a mass smaller than the original nucleus. This process is known as nuclear fission. We knew all of this, right? Well, almost all of it. We didn't know the year was 1939. We didn't know that it was these 4 Germans that discovered this. But that's really extraneous, right? Okay, we don't need that stuff. It's the other stuff that we need. Here's a couple possible fission reactions that can occur. There's more, but here's 2 that can occur. The first one, this is the one that we used as an example in class. Although notice, they have it listed as a 2-stepper problem. A uranium nucleus plus a neutron goes to uranium-236, and then that in turn goes to barium-141 and krypton-92. I explained to you that that there's for a very, very short period of time, uranium-236 produced, right? The neutron gets absorbed. It becomes uranium-236. And then it breaks apart into barium and krypton. Usually, it doesn't really matter about that middle step. They have it labeled here, so we'll go with it. Second one says a neutron plus uranium-235 goes to xenon and strontium. So 2 different things. Still lighter than the original, still nuclear fission, plus some neutrons. How many neutrons do we have? Well, here's what I want you to do. Look at this or look at this. It doesn't matter. In both cases, you can see the mass number is 236, the atomic number is 92. And on the right-hand side, you know it has to go to 236 and 92. Let's forget about the neutrons for a second. 140 plus 92 gives me 232. And 54 plus 38 gives me 92. All right, we're missing something. What are we missing? Missing some neutrons, right? But how many neutrons are we missing? 4, right? You can't say 4, 0, because that's not a particle. But rather what you can say is 1, 0, which is exactly what they've already said, times 4. Be careful here. Don't say times 3, because we've already have 1. We just need to add 3 more, right? Well, we're not adding. We're multiplying. If we already have 1, we've got to multiply it by 4 to get 4. So the answer would be A for that. Is that good? Let's take a look at these ones as well, actually. The information says the measurements given below indicate that uranium-235 has a smaller mass than the mass of the protons and neutrons. Okay, that was our second definition for mass defect, right? The mass of the protons and neutrons is more than the mass of the nucleus. The mass of the nucleons more than the mass of the nucleus itself. Okay, the difference in mass is called mass defect. They tell us that, although we already knew that. Einstein's concept of energy mass equivalence can be used to predict the energy that binds a nucleus together by using the mass defect. Got a massive uranium-235, massive proton, massive neutron. How do you find the mass defect here? This is not exactly like the question that we just did. Right? It's not exactly like this, because we don't have a reaction. We just have a nucleus with protons and neutrons. So how are you going to tackle that? Kyle, what do you want to do to start this one off? No? What was the second definition of mass defect? They give it to me up here, right? The difference in mass between the nucleus and the nucleons. So let's get the mass of the nucleus. Oh, wait, we already have it. Let's get the mass of the nucleons, the protons and neutrons. There is 92 protons in this. So we're going to say it's 92 times 1.6726 times 10 to the minus 27 kilograms. Get the mass of the protons. Does that make sense? Now let's get the mass of the neutrons. There's 143 neutrons. So the mass of that is going to be 143 times 1.6749 times 10 to the minus 27. We get a mass of the neutrons there. Add those up. Add the protons and neutrons up. What are you going to find? How's that number going to compare to that number right there? Protons and neutrons will be heavy. Subtract the 2. Protons and neutrons, the nucleus, subtract the 2. That's going to be your mass defect. Cal, does that make sense? Once you get the mass defect, the next question should be easy. Once you get the mass defect, Kate, how are you going to find the energy that's equivalent to the mass defect? Good. Now remember, when you do that, you're going to get an energy in joules, which you're going to want to convert to electron volts there. Good.